Just a few days ago, on the night of April 22nd, millions of people looked up to catch the peak of the Lyrid meteor shower. It's a beautifully romantic sight. A glowing shooting star silently streaking across the vast, dark cosmic canvas. People clasp their hands and make wishes, but unfortunately, the universe doesn't care much for romance. That beautiful streak of light, it's an intensely compressed shockwave of blazing plasma. Welcome to the real physics of a shooting star, and 2026 gave us an absolutely perfect laboratory to witness this cosmic phenomenon. Usually the moon ruins the show by shining too brightly, but this year it gracefully set right after midnight, leaving a pitch-black sky. This allowed observers to clearly see the Lyrids, one of the oldest known meteor showers, putting on a spectacular, flawless light show. But what exactly are you wishing upon? A giant flaming rock plummeting from the heavens, ready to crush our tiny planet? Not quite. Let's zoom in. Way in. To understand a shooting star, we have to look at something surprisingly small. In astronomy, before it hits the atmosphere, it's called a meteoroid. And for the Lyrids, these meteoroids are shockingly tiny. We are talking about a piece of space debris no bigger than a green pea, and often just the size of a grain of sand. Yes, that massive, brilliant streak of light that you can see from dozens of miles away is created by a cosmic speck of dust. So, how does a harmless little grain of sand create a fireball bright enough to outshine actual stars in the night sky? The answer lies in kinetic energy. This tiny speck isn't just falling, it is screaming into our atmosphere at an unbelievable speed. According to NASA's Meteoroid Environment Office, the Lyrid meteors hit our atmosphere at a blistering 49 kilometers per second. That is 110,000 miles per hour. Fast enough to travel from New York to Los Angeles in under a minute. So, where exactly do these hyperspeed cosmic sand grains come from? They don't just appear out of nowhere. They are the discarded breadcrumbs of a massive ancient traveler. A ghostly wanderer known as Comet Thatcher. Officially named Comet C 1861 G1, Thatcher is essentially a gigantic frozen dirty snowball tumbling through the darkness of space. Unlike the planets that orbit the Sun in neat, nearly circular paths, Comet Thatcher takes a highly elliptical, eccentric route. It plunges into the inner solar system, whips around the Sun, and then slingshots way back out into the deep cosmic freeze. This epic journey takes an incredibly long time to complete. Exactly 415 Earth years for a single orbit. The last time this icy ghost visited our neck of the cosmic woods was back in the year 1861. To put that into perspective, the world was a very different place. The first transcontinental telegraph was just being built across America. During that close approach, the intense heat of the sun blasted the comet, causing its ancient ice to rapidly melt and turn into vapor. As it vaporized, it shed massive amounts of trapped dust, tiny rocks, and gas into the void, acting like a giant cosmic litterbug. It left behind a massive, invisible river of debris, a dusty trail suspended perfectly in the silent vacuum of space. The comet itself is long gone, currently floating somewhere in the outer solar system and not due back until the year 2276. But its dusty footprint remains. And as if on a strict cosmic schedule, every single year in late April, Earth's orbit intersects this ancient trail. Our planet literally plows right through this suspended river of cosmic dust at tens of thousands of miles per hour, acting like a giant vacuum cleaner. So, when you watch the Lyrids, you are actually seeing Earth sweeping up a 400-year-old icy ghost's glowing footprints. Now, our tiny grain of sand is hurtling towards Earth's atmosphere. And here is where most people get the physics completely wrong. We are taught in school that shooting stars glow because of friction. Kind of like rubbing your hands together very fast to get warm. But at these extreme cosmic speeds, simple friction is actually not the main culprit behind that massive fireball. In the upper atmosphere, where meteors first ignite, the air is extremely thin. The molecules are just too far apart for simple rubbing to do the trick. The real underlying phenomenon powering this beautiful light show is an aerodynamic principle called ram pressure. Imagine moving your hand through a pool of water. If you move slowly, the water has time to easily flow around your fingers. But if you slap the water incredibly fast, the water molecules can't get out of the way in time, and they pile up against your hand. The same thing happens to our tiny space rock. Because it is traveling at 110,000 miles per hour, the air molecules literally do not have time to move out of the way. Instead, they get rapidly squeezed together right in front of it. And a fundamental law of thermodynamics states that when you rapidly compress a gas, its temperature rises dramatically. It's like how the barrel of a bicycle pump gets warm when you force air into a tire, but happening on a cosmic extreme scale. This massively compressed pocket of air in front of the meteoroid gets superheated to absolutely mind-boggling temperatures. We are talking about temperatures reaching around 3,000 degrees Fahrenheit, or roughly 1,650 degrees Celsius. At this extreme heat, the compressed gas stops being normal air entirely. It transforms into a brilliant glowing state of matter called plasma. So, when you see a shooting star, you aren't actually seeing a rock burn. You are seeing a tiny rock pushing a blinding wall of plasma. So we have this blinding, superheated plasma shield pushing through the atmosphere. But what is happening to the tiny sand grain hidden inside? As it rides right behind this wall of extreme heat, the temperature of the cosmic rock itself begins to rapidly skyrocket. This immense thermal energy triggers a dramatic and transformative process known in astrophysics as ablation. During ablation, the extreme heat causes the outer layers of the meteoroid to literally melt and transform into vapor, peeling away into the sky. Think of it like rapidly peeling an onion layer by layer. But instead of onion skin, it's shedding glowing layers of liquefied ancient rock. In fact, the heat is so intense that much of the rock bypasses the liquid phase entirely, sublimating straight from a solid into a gas. This rapid vaporization is what truly fuels the light show. It transforms the solid piece of ancient comet into an expanding cloud of particles. As these newly vaporized rock particles shed off the main body, they violently collide with the atmospheric plasma shield, pushing against them. This high-speed collision creates a massive elongated wake of glowing, ionized gas stretching for miles behind the tiny rock. This glowing wake is what astronomers call a meteor trail. It is the actual streak of light that we observe from the ground. Sometimes, if the meteoroid is large enough, this trail of ionized gas can linger in the sky for several seconds after the rock is gone. Eventually, the intense heat and ablation consume the rock entirely. Our brave little grain of sand gives everything it has to the atmosphere. It completely dissolves, transitioning from a piece of a 400-year-old comet into pure stardust and kinetic energy, leaving absolutely nothing behind but a fading streak of light in the dark sky, and perhaps a granted wish for whoever was lucky enough to be looking up at exactly the right moment. But if you were carefully watching the Lyrids this year, you might have noticed something extra special. They aren't just white. Meteors can actually come in a beautiful array of colors, acting like a natural high-speed cosmic fireworks display. This isn't random.
Meteor's tail holds a secret.
The color of a shooting star is actually a precise chemical fingerprint of the rock itself. As the intense heat melts the meteoroid, the different metals and elements inside it begin to glow, each emitting a specific wavelength of light. For example, if the meteoroid is rich in magnesium, it will paint the sky with a brilliant glowing blue or green streak. If it has a high concentration of iron, you will see a bright, vibrant yellow light piercing the darkness. And sodium? That element produces a warm, glowing orange color, very much like the light from old city street lamps. But the vaporized rock isn't the only thing glowing. Our own atmosphere joins in on the spectacular light show too. When the extreme heat of the plasma shield excites the nitrogen and oxygen molecules in the air, they emit a beautiful red and green glow. So, the final color you see from the ground is actually a gorgeous optical mixture of the glowing meteoroid and the excited atmosphere around it. The Lyrids are also particularly famous for a stunning visual phenomenon known as persistent trains. Sometimes, after the rock has completely vaporized, the trail of glowing ionized gas it leaves behind doesn't just fade instantly. It can linger in the upper atmosphere for several seconds, or even minutes, twisting and glowing faintly in the high-altitude winds, like a ghostly ribbon. These lingering, beautiful trails are exactly what allowed ancient stargazers to track and study the Lyrids long before modern telescopes existed. And that brings us to a fascinating fact. The Lyrids hold a very special ancient record in the history of human astronomy. The Lyrid meteor shower is officially the oldest recorded meteor shower in human history. To find the very first written account of this specific cosmic event, we have to travel back in time over 2,700 years. The year is 687 BC in ancient China. In a historical text known as the Zhuojuan, astronomers made a beautiful, poetic, and incredibly accurate observation. They documented that during the middle of the night, stars fell like rain. They didn't have modern telescopes. They didn't know about Comet Thatcher, or aerodynamics, or superheated plasma, but they stood beneath the exact same dark sky, gazing at the exact same glowing cosmic debris that we do today. Think about that for a second. Countless generations of humans, spanning millennia, have all shared this exact same cosmic light show. While human empires rose and fell, our icy ghost, Comet Thatcher, just kept quietly doing its massive orbits, dropping a fresh trail of dusty debris for Earth to sweep up every single April. Like a reliable cosmic clock, it connects us across the vastness of time. A shared human experience written in glowing plasma and stardust. But wait, this beautiful poetic connection actually brings up a rather alarming scientific question. If Earth acts like a giant vacuum cleaner, plowing through this trail every single year and burning up millions of particles, won't the trail eventually just run completely dry? Won't we just run out of shooting stars? Could there be a day in the future when the night sky goes completely dark and the Lyrids vanish forever? To answer that terrifying question, yes, the Comet Thatcher debris trail is technically finite and will eventually run out, but not anytime soon. But here is an even crazier scientific fact. Earth doesn't just collect space dust in April. We are constantly flying through a cosmic haze. Every single moment of every day, invisible specks of ancient space rock are drifting down through the atmosphere, landing gently around us. These are called micrometeorites, and according to NASA, Earth sweeps up an astonishing 40 to 50 tons of this cosmic material every single day. That is equivalent to several fully loaded school buses of alien rock raining down on our heads, completely unnoticed, year after year. Because they are microscopic, they are entirely harmless. But what happens if a piece of comet debris is bigger? Say the size of a bowling ball. This brings us to our final terminology check. In space, it's a meteoroid. In the sky, a meteor. But if it survives and hits dirt, it is officially called a meteorite. And suddenly, our beautiful cosmic light show becomes an invisible, high-speed projectile threat. What are the chances of one of these ancient rocks crashing through your living room roof while you sleep?
Imagine
Should you
a
be
giant
terrified?
lottery wheel with millions of
Well,
losing tickets for
statistically
every win.
speaking, the
odds
odds of a
hitting the jackpot are
meteorite
incredibly
striking
low.
a human
This spinning
are
wheel shows the
astronomically
scale of the
low. You are far more likely to win the lottery, get struck by lightning, and find a pearl in an oyster, all on the same day. Though, to be fair, houses and cars have occasionally been safely dented by falling space rocks throughout modern history. It is rare, but real. Fortunately for stargazers, the particles in the Lyrid meteor shower are simply too small and moving too fast to ever survive the journey. So you are perfectly safe standing in your backyard enjoying the show. But what about the future of the show itself? Will the Lyrids continue to light up our April skies forever? The short answer is no. Over thousands of years, the immense gravitational pull of giant planets like Jupiter constantly tugs at this debris. What was once a dense, concentrated cosmic highway of sand grains gradually gets scattered and dispersed across the solar system. Eventually, far in the future, Earth will cross this exact point in its orbit in late April and catch absolutely nothing. The sky will be quiet. The blazing 400-year-old ghost of Comet Thatcher will have finally faded into cosmic history. It is a beautiful, humbling reminder that the universe is not a static, unchanging painting. It is a wildly dynamic, moving environment. Everything we see, from the smallest meteor to the largest galaxy, is temporary. The ancient astronomers saw a much richer shower than we do today, and our distant descendants might look up and see nothing at all. So the next time you see a streak of light, remember what you are really witnessing. Not just a falling star, but a tiny grain of ancient ice pushing a blinding wall of superheated plasma at 110,000 miles per hour. A violent, spectacular, and beautifully colorful end to a solitary journey that lasted millions of miles in the freezing dark. And we are incredibly lucky to be standing exactly here on this tiny blue dot at exactly the right time in cosmic history to witness it. Thanks for exploring the violent beauty of the universe with us. Stay curious and keep looking up.